Welcome to breadboarding. In the previous video, we looked at the monitor and some of the example programs. And in this video, what I'm going to show you is how to write a very simple Hello World program in machine code. In fact, it's not world because we've only got 6 digits on the 7-segment display. So we're only going to be showing hello, in fact, in this particular case. But what I'll be talking about is the architecture of the 6809 processor, how the registers and the instructions are organized. And this is very similar to most other microprocessors. They only vary really in the number of registers, and the naming of some of the registers are different. In fact, even modern processors like the latest Intel and ARM chips have very similar naming of registers. Perhaps they might have 16, 30 or more registers, but the concepts are still the same. We're just going to have a quick look at the data sheet. So this is the 6809 data sheet. And what I just wanted to show in here is it includes information about the basic structure of the microprocessor. So you can see here what it's showing us is that you've got the program counter, which controls where the next instruction is. The accumulators, the A and B accumulators, are where we do most of the work, where we load things to and from memory, where we do arithmetic and other logical operations. We also do tests and things on values which are in the accumulators. The A and B accumulator can be treated as a single 16-bit value as the D accumulator. We then have some other important registers. So condition code register is where we get a lot of the status information, where we can disable interrupts, where we can tell whether a result has overflowed, whether a value is 0. The direct page register is used to provide a more efficient addressing mechanism, which it reuses a smaller number of bytes. So rather than needing 2 bytes for an address, the direct page instructions take the most significant byte value from the direct page register, and then the least significant byte comes from the following next byte after the instruction. On the 6502 and 6800, the direct page register was effectively set at 0, so you could only access the first 256 bytes of RAM using direct page instructions. 6809 allows you to move that direct page pointer to anywhere in the memory. So it just allows us to access data a little bit more efficiently. There are general purpose X and Y registers. So these are 16-bit registers which are normally using for pointing to addresses and things. You can do calculations on them. And then there's the system stack pointer and the user stack pointer, and these are used for pushing and pulling register values into memory, and particularly will be used for passing parameters between subroutines. In particular, if you're using things like C, for example, then C will make quite a lot of use of stack pointers for passing variables around. So most processors will have a program counter, will have accumulators, will have index registers and stack pointers. It just depends on each processor what exactly they're called and how many they have. So one of the key things about the 6809 is it has a relatively small number of instructions. I think it's about 59 individual. Yes, it's 69, but 59 basic instructions. But it has an awful lot of addressing modes. That means that the way how the instructions can be used is very, very flexible. I'm not going to go through all the addressing modes now because it would take probably a whole video in itself. But needless to say that there's a lot of different ways how we can use the instructions to access values immediately following perhaps the instruction, or pointing to other areas of memory where we get the values from. And the indexed addressing in particular is particularly complicated and powerful. And we'll be using this page here a bit later on. And this is how we create the second byte on index instructions. So it tells us exactly how we should use the index registers, whether we should do offsets. We're able to increment and decrement values before and after we use them, and all sorts of clever things. Now, really, this is where, if we're doing machine code of handwritten, this is quite complicated. If we use an assembler, then the form of these addressing modes in assembler makes it much easier, and all this sort of stuff that's taken care of for us. So there's a lot of addressing modes. We're only going to be using some very basic ones to start with. Let's see what else we've got here. There's other information about pushing and pulling. So when we call a subroutine, for example, what we're able to do is save the state of all the current registers we have to the stack, and we can also pull values off the stack. So we push values onto the stack and we pull them off. There's also instructions for transferring and exchanging register values. The load effective address instructions are quite handy, and we'll come to those in later videos. And then in particular, we've already mentioned software interrupt. The software interrupt instruction allows us effectively to set a breakpoint and go back to the monitor to inspect variables and things. Now, there's quite a lot of detailed information in flow diagrams and things that show how the instructions are actually executed, but we don't really need to go to there. Here's a summary table of the basic instructions. A few more there with all the various branch and miscellaneous instructions, and then there's tables and tables worth of hexadecimal values, which shows us the hexadecimal machine code we actually need to tell the computer to do what we want it to do. Now, if you use an assembler, we don't really have to worry about all of this. We just use these mnemonics, the letters, and with the modifiers for addressing modes and things, and the assembler takes care of converting that sort of human readable form into these sort of binary codes. But because we're going to do things in machine code initially, and we're not going to use an assembler, what I've done, and this is something I used quite a lot in the past, in my early days of programming, where we had to use machine code, is actually creating a grid. This grid here has, I think, the most significant byte first, then the least significant byte, and then we've got all the various mnemonics here. So, for example, load A from the byte following, so a sort of immediate mode. So load A with the next byte following it is 86, for example. And what I have done here is the ones that we're being using for the instructions we're going to be using for this simple machine code hello world, I've actually circled already so I can find them. And you see there's quite a lot of them, and there's some on the other side as well. Some of the instructions actually require an additional byte, so 10 or 11x preceding it. And that tends to be for the Y, U, and S instructions tend to need more. The X register tends to have shorter instructions. So in general, it's better to make more use of the X register rather than using the Y, just because the instructions are a little bit shorter. And then, as I showed you previously, this is then for indexed instructions. The post byte following the instruction tells it exactly how it should do the indexing. In some cases, it might mean there'll be further bytes following on from the instruction. But this is what we're going to be using these sheets for doing our hand assembly. We could access the data sheet like this, but it's a little bit cumbersome for that purpose. Well, I should just say, if you want to know about assembly language programming, I learnt about programming by this 6809 assembly language by Lance Leventhal. I believe this is available as a PDF download. I have the original. This is a very good book. If you want to know assembly language programming, then I'd strongly recommend you get a copy of it, or you at least download the PDF. I'll include the PDF link in the comments, but this takes you through everything from hexadecimal, about assembly language, and takes you through the basic architecture of the 6809, and has lots and lots and lots of good examples, and includes sections on even how to interact with peripheral interface adapter, how to handle interrupts, and how to work with serial ports and things like that. So the Lance Leventhal 6809 programming, I include the links for it. I'd strongly recommend, if anyone's interested in this, to grab a copy of that. In this slide, what I've got is some information about the program we're going to be writing. So what we want to do is to display hello on 5 of the digits of the 7-segment display. Now, in fact, in the data sheets, or the original project sheets, the original 6802 version stored the 6 digits was actually in the direct page area in the first 256 bytes of RAM. But in fact, on the 6809 nanocomp, it's actually stored in this area here. I don't believe it's actually in the Wireless World magazine article, but since I've already disassembled the monitor previously, then I know where these are located. What we're going to want to do is, for each of the hello, we need to work out which segments need to be illuminated. So a 1 in the value, in fact, will turn the segment on. And so, for example, if we have a value, we've got B0, 1, 2, 3, 4, 5, 6. If all those values were 1, we'd actually have a value of 7F in hexadecimal. That means the bottom 7 bits of that character are all 1. So in fact, when we look at what bit 0, bit 1, 2, 3, 4, we can see these are the values. And in fact, when we look at H, it means that B3 and B4 will be off. So if we have 7F and we might take away the values for B3 and B4, we end up with 6, 7 hexadecimal. For E, we need to take away the B1 and B2. So B1 and B2 is combined is 6. That makes 7, 9. For L, we're only going to have B4, B5, and B6. So that gives us 7, 0, B4, B5. So that's 1, 2, 3. So that's 7, 0. And for O, we've effectively got all the segments without the middle one. So that's B0. So that's just 7E. So these are the character values, the 7 segment display values you want. And then the final one will be 0, 0. And then the final thing we need to know is, as published in the original Wireless World article, the disp-resh or display refresh subroutine is at 7C, 7B. And what this does is it takes the values of each of these memory locations and it sends the information out to the peripheral interface adapter from value 4, 5, 6, 7, 8, 9 on port B, and then we'll take the 7 segment display value here and put that on port A. So what it will do is effectively display the values from memory to the display, and I think it includes some delays in there, so it does it for a couple of milliseconds. So what we're going to do in our initial code is, once we've set up the values we want to display, we're just going to call the display refresh routine continuously until such time as we press reset or abort. That's what we need to do for the program. So we have here the values that we need to put on display. And what I'm going to do now is just to show you how we can do this in machine code, just with hand assembly, without any computers whatsoever. And this is what this Nanocomp trainer was originally used for. Before people had proper desktop computers, this was all that you had. So let's start our simple Hello World program. So to start with, I'm just going to use the assembler mnemonics. And then what we're going to do is then allocated addresses to each of the rows, and then we'll hand assemble the mnemonics into machine code. So first of all, what we need to do is we're going to need to have, first what we're going to do is to load the character values into the A register, the accumulator, and then we're going to use that to store them out to the memory locations for each of the digits. Now we could do this in a loop, but we're just going to keep it really simple to start with and just do it with kind of hard-coded values to start with. This is Hello World. We're not trying to boil the ocean here. So what we're going to do first of all is load A. And we want to do this immediate, which means we load the value next in the next byte. So 6, 7. Then we need to store that at first digit. So we're going to store A, and this is going to be extended, which means we're going to put the address in the next 2 bytes. So 13F. So what that does is loads 6, 7, which is H, into A, and then stores A to here. So we're just going to repeat that for these other characters. So load A with 7, 9, and the dollar means it's hexadecimal rather than decimal. And store A at 13FB. Then the next character we're loading is going to be twice, so the L is 7, 0. So we're going to load that once, and we can then store that twice. 13FC, and then we can store A again, 13FD, We've done the 7070, so we've done that one, that one, that one, and that one. Now we need to do 7E. Load A. It's 7E. We're going to store that at 13F E, and then that, and then we just need to store 0 at 6. So what we can do there, we don't actually have to load A with 0. What we can do is use an instruction which is called clear 13F. What that does is move 0 into 13FF. Once we've done that, we've loaded all of the values into the display there. So now what we need to do is to call the subroutine that refreshes the display. So if you remember, that was the display refresh at 7C, 7B. So what we're going to do there is jump subroutine 7C, 7B. And when this returns, what we're going to then want to do is just jump back around and do that again. So in fact, what we're just going to do here is jump, and we're going to specify the address here, which is going to be, let's just call this end. We just want to jump to end. Now we don't know what the address is yet for that. Okay, so that's our pretty simple machine code. So this is mnemonics, and this is what we would normally write assembler in, and we might use labels and things to specify the addresses. And typically what we might have done is actually specify labels also for those as well, and probably we'd do defines for these other things, so we don't have to refer to things as 6, 7. We'd refer to it as character H or something like that. Right, so what we're going to do now is look at the, so this is the machine code instruction set sheet I've created. You can go through the data sheet, but it's a lot easier when you're doing this to use this type of sheet. So what we're going to do here is actually look up, this is the most significant byte, this is the least significant byte. So for example, load A immediate, so you see immediate here, it's got the hash in there. So load A is 86. So what we're going to do over here is just to write out the bytes. So we're going to start this at 1000, which is the start of our memory. And then we're going to, this is 868667. Now, what we then have to do is say that's 0, that's 1, so the next address will be 1002. You see, until we actually do this hand assembly, we don't really know how many bytes we're going to have for an instruction. The next thing is store A extended, that means use the next 2 bytes. So store A, that is B7. B7, and then we've got 13, then A. So you can see now that we've got 3 bytes there, so that's 2, 3, 4, so it's 1005. Then we've got load A with 79, so that's going to be 8679. Then, so that's 6, 5, 6, 7. 1007. Store A 13FB, so that's B7 13FB, and that's going to be 789A. So we're doing everything in hexadecimal here. So load A with 70, that's 8670. Then we're going to store this twice at 13FC and 13FD. So that is ABC 100C. That is going to be B7 13C CDE F. F. That's B7 13 F. And this is about the most inefficient way of doing it. I'm not suggesting this is an efficient way of doing this, and we'll perhaps look after this once we've got it working of perhaps how we might do it in a slightly more flexible way. But let's just get this working first. That's F, then it goes 10, 11. This is 12. And this is load A with 7E. So that's 8, 6, 7E. And then 10, 2, 3, 4, 1, 4. And this is store A again, B7, 1, 3, F, E. Now we come to the clear. So clear extended, so this means clear the memory location provided in the next 2 bytes is 7F. So this is 4, 5, 6, 7, 1, 0, 1, 7. So clear is going to be 7F, 1, 3, 1, 3, F. Now we come to our jump subroutine, and the label here is going to be, this is 7, 8, 9, so this will be 1, 0, 1, 0, 1A is jump subroutine 7C, 7B. So let's look for jump subroutine. Again, jump subroutine here with the following 2 bytes is BD. So BD 7C, 7B, and that's the monitor routine that refreshes the display for a few milliseconds. And then A, B, C, this is 1, 0, 1D. Then what we're going to do is jump back to 1, 0, 1A. So we can now put that in there, 1, 0, 1A. Let's jump back to end. So jump is 7E. Okay, so 7E, and then we're going to do 1, 0, 1A. Right, so I think that's our program. We just count how many bytes it is. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it's 32 bytes. Of which really 6 of these are the character values. So really we've got about 6 and 32, so we've got 26 bytes of code. Okay, 26 bytes of code. So what we're going to do now is to type that in, see if we can get it working. Right, so we've got the NanoComp started up. The voltage is about 4.78, so it's getting on a little on the low side, but it should be fine. What we're going to do now is to type this in. Normally when I do this, I'll put it in and then review it afterwards just to make sure we've not made any mistakes. So we've got 8667, B7, 13, FA, 8679, 1007. Yeah, that's correct. So it's always worthwhile checking the address just to make sure you haven't missed out entering a key. So then we want B7, 13, FB, 0A, 8670. 7010C, B7 13C, B7 13FC, then B7 13FD, B7 13D, main run 12 02 012, 867E, 6 7E. Then 414 is B7, B7, 13, FE. And the final one is clear, 13FF, so that's 7F, 13, FF. Then we've got our jump subroutine, so that's BD, 7C, 7B, and finally 101D, 7E, E, 101A. And you can see obviously if we'd got our address range wrong here, and we'd end up with the wrong values in the wrong cells when we come to the jumps and things won't work. So we're now ready to run it. So what we should find is we get hello. Excellent. So that's working. Hello world in machine code. as I said, this is not the most efficient way of doing a machine code. And what I'm going to do now, I'm just going to rewrite this more in the way how we would typically do this, and where we'd probably we'll put the text going the message in a separate area of memory, and then we'll write a loop to display the message. This is probably more like what we would do in real life. It's not going to be massively shorter in code size, but it probably allows us to extend. If we needed to extend the display, say, to 20 characters, then it would scale up, whereas this obviously would not scale very well. What we're going to do now is to create a better version of our Hello World machine code. And this one, we're actually going to use the X and Y index registers, and we're going to be using the auto increment feature of those, so that once we've used the register, it automatically moves on to the next memory location. So what we're going to do is to use the Y register is going to be used for the display address, and the X register is going to point to the individual 7-segment codes. So what we have to do first of all then, and let's just put a label at the top here. So I just put start. So this is where I'll put the labels down here. And then we'll have the address, then we'll have the byte code, the bytes, and then we'll put the mnemonics down the right-hand side here. So we're using the Motorola 6809 mnemonics here. What we need to do first of all then is the X register. We need to load X, and we're going to load it with an immediate value. That is the value that comes after it, and we don't know what that value is. That's going to be the message. So that's message. We need to, and what we're going to do is put message down the bottom here. So we'll just do that now, shall we? Message, and we'll allocate an address for that at some time. And then that is going to have our message, which is H above, which is $67. Then it's $79, $70, comma, $70, comma, and $7E, and then followed up by 00 for the blank at the end. That's the message, and we'll give that an address. Normally, if you're using assembler, then these labels, the assembler would automatically resolve that when you're trying to load message in there, it would work out what the address is down here, but we're going to do all this manually. Then we're going to load Y, and this, we do know the address, that's 13FA, so that's the starting address of the first digit of the display. And then we're going to actually start a bit which we're going to call loop. And what we're going to do for each index, we're going to load A from X, but we're also going to add 1 onto it once we've finished with it. And then what we then need to do is to store that to where we're pointing to in Y. So we're going to store A for Y and add 1 onto Y once we've finished with it. And then after that, we need to make a decision about have we come to the end. Now, it's a little unusual this, and normally 00 or null is used as a terminator in C, for example. The only thing is here is that 00 in this particular case happens to be blank on the display, so equivalent of a space. Now, normally a space is 20 hexadecimal or 32 decimal. But in this particular case, we're needing to use 00 both to blank out segment 6 and also as the end of the message. When we store A to Y plus, if value is 0, then it will set the 0 flag in the condition code register. And what we can then do is to do branch equal. So if it's 0, it's equal, in other words, then we want to branch to the end. So we're going to have a label for the end. And the end code is just going to call the monitor subroutine to display the 7 segments, and then we just go around in a forever loop. So we need to put the offset for branch versus a relative offset. So we need to calculate that using our monitor example program. And then after that, we're now going to use a branch. So again, this is another relative jump, but this branch is going to go to loop. We want to branch to loop. Okay, so this is just going to jump back to loop, carry on, and when eventually it's done 0, then it's going to jump out and it's going to go to end. So then our next bit now is the end, the outside the loop. And what that's going to do is jump subroutine, and to that we're going to be calling the address immediately after. So 7C, 7B. So this symbol means extended address. So use the 2 bytes after the instruction. And then the next line after that, again, we're going to use a relative branch similar to the one we have there, and we're actually just going to branch back to end. So effectively, this is just going to go round and round in a loop at the end there until such time as we press reset or abort. Okay, so that's our program. Now what we need to do is to start allocating the addresses and work out the opcodes for this. So we're going to start this at 100 again, and load X with value there. So load X. So load X with the byte value immediately after it is what we want there, and that is 80. 8E, and then we don't know the 2 bytes after that yet, because that's going to be whatever address we give message. Okay, so the next one we need to do is then to work out what the next address is going to be. So that's 0, 1, 2, 3. So the next address will be 1003, and load Y with 13FY. Now that is in fact going to be a longer instruction, and when we look on the back here, that is 108E. So in fact, it's 8E, but with a 10 in front of it. So you can see that using the X register is slightly more efficient than, and then we're going to have 13FA. We just need to make sure we count these. So that's 3, 4, 5, 6. So this address here will be 1007 is loop. Now this one now is load A with an indexed address. If we look at our sheet again, load A with an indexed address is load A with R, which means it's an indexed address, comma R here. That is A6. So I'm going to put A6 there. Now, what we then need to do after that is in the data sheet, this shows this is the 6809 data sheet. This shows that there's a post byte that tells us which register to use and which of the many addressing modes we're going to use. Now, what I've done is, because again, this is quite complicated to work everything out, what I've got here is one where we've already worked it all out, and it's part of the same coding grid. So in fact, if we want, in this particular case, we want the X and then increment X after use, so post increment, and that happens to be 80. So we've got 80. Okay, so that's load A with X. So in the next line, so that's 7891009. Store A to Y++. Store A to Y++. I think that will also be store. There we go. So store A to a index register is A8. Sorry, A7. A7. That's A7. And now we need to find out what the post byte is for Y+. That is A0. Okay, so that says store A at the address of Y and then move Y on one. So once we've taken 6, 7 from there and we've stored it there, then the X is going to point to where we've got the 7, 9, and the Y is going to point to the next byte there. So that's all good. So now we need to work out what this address is going to be. So that's 9A100B. And we need to look at what branch equal is. So branch instructions are along here, and branch equal is 27. And then we're also going to have the offset, but we're going to use our built-in example program to calculate the offset. Okay, so then this is B, C, the next one is going to be 00D. And this is just going to branch back to loop. So what we need to do is to look at branch, and branch is 20. 20, and then whatever the loop value is. So then the next address down here is that's D, E, this will be 100F, and that's our end marker. Now the jump subroutine to 7C, 7B, that's going to be the same code we had to do, which is in the previous version, that's BD, 7C, 7B. And then finally, we've got another relative branch, and it's just going to jump back to the end label. So the branch was 20. And this address is going to be F101112. So 1012. So branch is 20, and we need to work out what the offset is. So that will just carry on going around there in that loop forever and ever. What that means then is that if this is 1, 2, this is 1, 3, so this is going to be 1, 0, 1, 4. So in fact, our message up here is going to be loading 1, 0, 1, 4. And now we've just got the 3 relative addresses to find out. So what I'm going to do is just switch the nanocomp on, and we'll run up the relative offset program. Okay, so I've got the nanocomp switched on, and if you remember, we're going to run the offset program, which is at 7A00. So it's going to ask us for the start address, and the first start address we're going to go with is, we're going from 100B, and we need to go to the end, which is 100F. So we're going to type in 100B, and then the end is 100F. And it's a 2-byte instruction. That's going a jump of 2. So if we think about that, 0, 2. So normally it would go to that next instruction, but in fact it's going to do 2 further. So it's going to go 1, 2, which is end. So that sounds like it's right. Then this one here is going to branch back to loop. So in this case, the starting address is 100D and the end address is 1007. The starting address is 100D and the end address is 1007. And again, it's a 2-byte one. So that's F8. Okay, so F8. That's a 2's complement number. So basically means the offset has all its bits reversed and then add 1 to make a 2's complement. So, right, so that's F8. And then the final one here is we need to do the branch back to here. So we're going to go from 1012, 1012, and we're going to 100F. It's 2-byte. Now we have to be careful here. That is actually FB, not F6. 6 would have the digit over the end there. So I've been caught out by that before. So this is FB. And that sounds about right because it's only a couple of bytes that we're going back. Whereas F6 would be almost 10 bytes that we're going back. Okay, so looks like we've got everything there. So what we can do now is if we just now go to 100, we're going to type this in, and then we'll go back and check it, and then we'll see if we can get it to run. So first of all, 80, 10, 14, the address down there. Yep. And 1003 is 108013FA. Then A680, A680, and A7, A0, 2702, and now we're on 00D, yeah, and this should be 20F8, 20F8. And we should be 100F, yes we are, and that is BD7C, 7B. Finally, 1012, 20FB, 20FB. Now we need to put in our message text, 677970. You see that 707E00. So let's just make sure we go back there again and make sure I get the right 677970707E00. So now we're going to run it and we should get exactly the same result that we had before. Hello, excellent, great. Now, the advantage of this one is that since we've got our message here, we could potentially change this. So if I wanted to change this message, say, to nanocomp, then what we might do is nanocomp 6809. And what I'm going to do is just check to see what the 7-segment codes are for that. So what we're going to do for N, we're actually going to use this sort of M character. C is going to be that. Then 6 is just going to be the normal 6. 8 is going to be the normal 8. 0 is that. And then 9 is, I think, that's, isn't it? And so codes for those are 6E, 78, 7D, 7F, 7E, 3F, and then we need a 00 on the end. Now the only issue with this is that because we've actually got 7 values here, the last 00 is in fact going to go beyond, where was the end here? The end here was 13FF. So in fact, the 1 byte beyond 13FF is 1400. So if we just look at what is at 1400 at the moment, that's 81 at the moment. So 1400 is currently 81. Okay. And what we'll expect this to do is, because the last byte here is going to be written to the next address after the display here, then we'd expect that to end up being 00 here. So let's just go in and change the values here. So 1014, 6E, there we go, 78, that one should be. 7D, 7F, 7E, 3F, 00. Okay, so let's try that again. There we go. So we've got nanocomp 6809. So you can see that this approach to having the message in separated out from the rest of the code does result in us having perhaps code that we can change more easily. And in fact, if we count out how many bytes this is, this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we've got 20 bytes of code, 20 code, 6 of data for the original hello. And if we compare that with the other one, I think we had, that's 26 bytes in total. We had 26 bytes of code and 6 bytes of character values. So I think you can see that this approach is a little bit more efficient, and the only thing we probably would need to consider would be having a length, perhaps, because we need to use the 7 segment data. We probably need to do this more by having a length as the first byte, perhaps to say only do this number of bytes, and that way we can have zeros and blanks embedded in the data. But it was an interesting way of doing this, just to sort of show the idea here. So I think what you can see here is that doing hand assembly of machine code is hard work, and it's quite error prone. What I'll show you once we've done the disassembly of the Nanocomp monitor and we're using the assembler, I'll show you this in the assembler, and you'll see that a lot of the hard work is actually done for us, and we'll leave that for a couple of videos time. So thanks for watching. I hope you found it interesting. Please hit subscribe if you don't want to miss out on any further videos, and if you can hit like as well, that'd be great, in that it helps to get the video in front of more people, promoted more by YouTube. So thanks for watching. Speak to you soon.